Yeah, comes on everyone. Let's start off. Sure, comes on everyone. Let's go ahead. The last thing that we did was this one, an infinite GP. So let's say we have a dumbbell here of mass 2m and m. It is unequal masses.
Oh,
Right, and these are like two fixed blocks. And let's say this E is equal to half and this E is equal to 1/3. So both of them don't have same restitution. And you're releasing them from a height h. Initially the rod is horizontal. Length L, massless rod. Right, so a rod is attached with two masses at the ends as shown. Is released from horizontal position. So this thing will come down and hit. So first thing, find the angular velocity. Tension in the rod just after collision. Find H max or central mass after collision. Let's get this. I hope the picture is clear. Because E is not same for both of them will bounce off with different velocities. This will make the rod rotate. So here a question mate is mentioned, so not sure what you're asking. When is the rod rotating? Initially, after you're asking? Initially, why will it rotate? Both are falling with the same speed. The rod will just remain horizontal, isn't it? Let's see. So this is 2m. This is m. Right? These are fixed. Now understand, on both of them, the gravity is g. They have same acceleration. They will have same velocity. The rod will just fall straight. Means at any point of time, the rod will remain horizontal. The rod will just fall like this. So when they're about to hit the thing, they will have a speed u, which is equal to root 2 gh, because the height is h. So this also will hit the ground with the speed u is equal to root 2 gh. Right? So Harry, what are you talking about? Mg will pass through center of mass, so torque is 0. Right. So so torque is 0. Center of mass is what? Center of mass is the point where the weight will act. So what will be mg? It will be 0. Clear with this? So both the balls will just come and hit the thing with the speed u root 2 gh. There will be no rotation initially because both have the same acceleration. After hitting, what will happen? Just now we saw, if you hit a floor with speed u, you'll bounce back with the speed of eu. Here e is equal to half and here e is equal to 1 by 3. So after collision, the 2m will bounce with a speed of u by 2 and this will bounce with a speed of u by 3. Right? And the center of mass will be somewhere here at a distance of L by 3. So the center of mass itself is going with some other speed Vc/m. You can calculate that also. So velocity of center of mass after collision will be 2m u by 2 plus m into u by 3 by total mass 3m. That will be u plus u by 3, 4u by 3, 4u by 9. That's your velocity of center of mass just after collision. Clear with this? We need that. Yeah, we need that to find h max of center of mass. So once you got that, you can find the maximum height of center of mass from here. That will be h max will be very center of mass square by 2g. So it will behave like its own particle. That will be 16u square by 81 2g. U ka value is root 2g, you can substitute. So that is one part of it. Now, how do you find omega from here? So how will this system actually move? Remember, there are no, other than mg, there is no other force. So your center of mass will continue to go in a straight line. So this is the path of center of mass. That is the whole definition of center of mass. If you remember, whenever you throw a system into there, the center of mass will be like a projectile. If you're throwing up, it will just keep going straight. And about this point, everything else is rotating. So as it goes up, now this guy is going with u by 3 and this guy is going with u by 2. So after some time, the picture will look like this. This will be m and this will be 2m. So this m is going in a smaller circle, and this small m is going in a bigger circle. So they're going in two different circles, right? And this circle radius will be L by 3. And this circle radius will be 2L by 3. Great. Now, how do you find omega? Now, listen to this carefully. How to find omega? Let's say we have two particles A, and let's say this is going with U1, theta 1. Let's say we have another particle here, B, which is going with U2 and theta 2, right? And let the distance be R between them. This is at any instant. Now, if you stop A, that is, if you do the problem with respect to A will think, okay, I came to rest. And now if you look at the components, this component will be U2 sine theta 2 minus U1 sine theta 1. This component will be U2 cos theta 2 plus U1 cos theta 1. So you can clearly see here, this is your V tangential. This is responsible for rotation. So the component perpendicular to the line joining is the V tangential here. Therefore, omega here in this case will be, so this is the omega angular velocity of B as seen by A. So if you ask A, what is B doing? It will say the relative velocity is U2 sine theta 2, U1 sine theta 1 by distance between them r. There. This is a general formula whenever you want to find omega between two particles. So if I use the same logic here, omega, the relative velocity perpendicular is u by 2 minus u by 3. I think I drew this wrong. Yeah, shape is wrong. 2m will go up because it is going faster. But okay, by distance between them is L. This is u by 6L. Or if you don't like this, you can go and stand on the center mass and find relative velocity and do that. It still works. So this is how the picture will be. 2m will be higher. M will be somewhere here. So 2m is going in a smaller circle. M is going in a bigger circle. Is the story clear, everyone? So this whole setup is rotating with omega. Then you're done basically. So if you take a person and make him stand on the center of mass, he will think everything is going in a circle with omega. So if you draw the free body diagram, he will say there's a tension T and there's a centrifugal force 2m omega square radius will be L by 3. Or you could do the other one, tension T, and here the centrifugal force will be m omega square 2L by 3. It doesn't matter. You can take any one FBD. You will get the same thing. There you get tension is equal to 2m omega square L by 3. Omega is nothing but u square by 36L L by 3. This will be mu square by 54L. Check. That's your answer. That is the tension in the rod after the collision gets over. Are the steps clear, everyone? Why will the balls don't interact with each other? Since both have same velocity, tension in the rod is 0 initially. There is no horizontal velocity. So when they're falling, there'll be no tension in the rod. After hitting, you'll get a tension because both are going with different velocities. The rod will start pulling them. The center of mass will continue to go in a straight line, and both the things will start rotating about it. Clear with this? MGH by 27. 18 threes, na? 54. Right, Utsa? Okay, you substituted the Yuka value, right? You can substitute U as root 2gh. Perfect. All clear with this? It's a good one. You can see how many things are there. There's a collision, there is a rotation, right? Omega. I think this is, you can put this thing actually. This is the angular velocity of A with respect to angular velocity of B with respect to A. So this is how you find angular velocity if 2 points are given. This actually we could have added in the circular motion also. Remember this? Let's see one more. Let's see, this is a little different. This is an impulse-based problem. Let's say we have a ball of mass m. This is a top view. We have another ball of mass 2m. And let's say we have another ball of mass m. So let's call them. I'll do one thing. Let's make it 3m. So that there'll be no confusion. So this is A, this is B, this is C. The length of the string is L. L. This angle is 60 degrees. This is the top view. Everything is placed on a smooth floor. So there's no friction, no gravity, nothing. Then what you did, you kicked this ball A with an impulse J. So what is impulse? You know, when you're playing caroms, right? When you hit the striker, that is an impulse. When you suddenly give a jerk or something, it's called an impulse. You suddenly hit it. So then what will happen when you hit this A, right? This will start moving. So the picture will look like this. First, the string will become loose. A will go like this, then the string will still be loose. A like this, then string will become tight. When the string suddenly becomes tight, B and C also will start moving. So find the velocity of A, B, C when the string just becomes tight. Find the velocity of A, B, C just after string AB becomes tight. So initially strings are like there is no loose string or anything. It is just fit. I hope the question is clear. So initially when you hit A, nothing will happen. Initially it will be like this, loose, loose, and then when it makes 60 degrees, it becomes tight. When this string suddenly becomes tight, this string also becomes tight. So the whole thing will start moving. So let me say when just after strings become tight, that is a better word. This is not an elastic collision. This is something else, an impulse based. Let me help you. See. So how will your picture look like? Always draw your picture first of all. So this is 3m. This is 2m. This is m. You gave an impulse j. So j is equal to mv. So basically this thing will go with the speed v. Remember, this tension will be 0, this tension will be 0 because the string is going to become loose. Then your picture will look like this. So this is 3m, this is 2m, this string is still loose. So you're still going with the same speed v. Then this is 3m, 2m. So again, when the length becomes this, now the strings become suddenly tight. This will have tension T1. So this will pull with tension T1. This will be tension T2. This will be tension T2. That is how the velocities will become. And what will be the angle there? You can clearly see here, if this is 60, this is 30. So it makes 30 there. So this total angle becomes 120. So I'll just put this as 30. That is how your picture will become. Now, when the string becomes tight, how will the velocities be? Now, 3m, if you look at right, on 3m, let me just draw that again. So now if you look at the velocities, so velocities will change only in the direction of the force, isn't it? Now, on 3m, the only force acting is T2. So let this velocity be V3. On 2m, now there are two tensions acting, T2, T1, both are acting. So I'm not sure how it will go. So when we're not sure how it will go, we will take Vx and Vy. We will take two velocities because 2m can go in any random direction. What about m? M is interesting. If you look at this velocity V, right, only the component of velocity along the tension will change. That means the perpendicular component was unaffected. So in this direction, the component will be unaffected, which will be how much? This angle was 30. So that angle was 60. V cos 60, V sin 60. And in this direction, we will get some other velocity. Let's call it V1. So since tension is perpendicular, T1 is perpendicular to V sin 60, it is unaffected. We have done something like this. Remember this question? When the string suddenly becomes tight, the tension was in this direction. So this U sin 30 didn't change, only the V dash changed. Hope you remember that. Right? So this is how the picture will look. Clear. So let's do this. So how many variables are there? V1, V3, Vx, Vy. So we have 4 unknowns. So I need 4 equations. If I get my 4 equations, my job's done. So first equation here. So impulse due to T2. So T2 dt, force into time, must be change in momentum, which is 3m into V3. Now, if that integral is scaring you, you can just put something called J2, which is nothing but impulse due to T2. So J2 is impulse due to tension. What is impulse? Force into time, change in momentum. Right? So J2 is 3m V3. Now, if you look at 2m, this angle was 30 degrees. So in the horizontal direction, integral T1 sine 30 minus T2 dt is equal to 2m Vx, the horizontal component. Again, so you can write this thing as integral T1 dt as J1 sine 30 T2 dt is J2, which is 2mvx. This is your equation 2. Again, remember, we don't know what is J1, J2, they will cancel off. So this is for 2m in the horizontal direction. This is for 3m horizontal direction. For the 2m in the vertical direction, there is only one impulse, which is integral T1 cos 30. So that is the force in the vertical direction into time will give you 2m Vy. You can write this thing as J1 cos 30. And then for this guy, for m, just give me a minute. Now for m, that component is anyway fine. That will be minus T1 dt, that is in the opposite direction. Initially, what was the velocity? Initially, if you remember, this component was v cos 60. Let me put it in black. This was v cos 60. This was v sin 60. So v cos 60 became v dash. That will be change in momentum, which is m into v1 minus m into v cos 60. So this is minus j1. So we get j1 will be mv by 2 minus mv1. This is equation 4. Totally, how many variables are there? j1, j2, v1, vx, vy, v3. We have 6 variables now. Because you took T1, T2 also, na? So I need total 6 equations. I got 4. Where will I get 2 more from? These all are, if you see, just change in momentum. Impulse is equal to change in momentum. Force into time is change in momentum. How much is the time? I don't know. How much is the force? I don't know. So J1, J2 are unknowns. We still need 2 more equations because there are 6 variables. Are there any external force on the system? That means velocity of center mass will remain constant or horizontal momentum is conserved. And there is one more thing. Oh, we said it. Velocity along the rod must be same. String constraint. So we get 2 more equations. Let me write them in the next page. This thing comes from the string constraints. If you like this line, velocity along the string must be same. So we will get v1 must be equal to vx cos 60 plus vy cos 30. This is your equation 5. And horizontal momentum is conserved. So initial momentum was m into v. Now the final momentum will be 3m into v3 plus 2m into vx plus m into this is 30 and this is 60. v1 cos 30, v sin 60 cos 60, the horizontal component. And this is your equation 6. It's pretty lengthy to solve though. There, you have 6 equations, 6 unknowns. If you solve, you will get the answers for v1, vx, vy. I could have made the numbers little more easier. I could have made the question more easy like this. Keep them like this and give the impulse this way, j. That would have made your life easy. You will get 1 variable less. Iska ye component nahi hoga na, then you can say this velocity is in this direction only. That would have made your life little easier. But check your equations. If you got the equations, you can handle from here. First of all, is this picture clear? How will the diagram look? So string will become loose, and once the ball goes to the other side 30 degrees, then it will become tight. So the T1 will pull M and 2M, and because 2M is moving, T2 will come, that will pull 3M. So this is how the velocities will look just after the string is tight. 3M will go horizontally, 2M we don't know how it is going, so we'll take Vx, Vy. The M will have two components, V sine 60 will not change, whereas the velocity along the string will change. Then we took momentum in the horizontal direction. So for 3M, the tension T2 is changing the velocity. So T2 dt, that's your impulse force into time. If that integral is scary, then we'll just write it as J2. So you see whatever is you are convenient. I too prefer to write every time in integrals, but some people see that integration and they get scared. So check your equations. All clear with this? These are some good ones, lengthy ones. This will be like a paragraph or something. You will need time. Great. Next thing. Let's go ahead. Oblique collisions. So we saw till now head on. Now, if your head on collisions are good, then oblique will be easy. So how do you solve? So what are oblique collisions? Velocities are not along the common normal. So how do you solve this thing? Step one, draw the common normal just before collision. So when the two balls or two spheres are about to hit, draw the common normal just before collision. Right? And then resolve the velocities along the normal and perpendicular to the normal. That's your step one. Step two, during collision, the forces will be along the common normal. So components along the normal will change. And the perpendicular components are unaffected. Then step three, to solve for velocities along the normal using head-on collision. So an oblique collision simply becomes an head-on collision plus perpendicular component. Solve for velocities along normal and add the perpendicular components. Let me show an example. So listen. So we have two spheres, M1, M2. This is your common normal. They're about to collide. I am giving little space. Let their velocities be u1, theta 1, velocities be u2, theta 2. So step 1, resolve the velocities along the normal perpendicular to the normal. The problem becomes like this. This. So the horizontal components will be u1 cos theta 1. This problem will be u2 cos theta 2. This component will be u1 sin theta 1. This component will be u2 sin theta 2. This is your head-on collision. And you know how to do this. How do you do this? Conservation of momentum, coefficient of restitution. So after collision, let the velocities be v1, v2. Conserve momentum, use restitution, find v1 and v2. In this process, these two components will not change. Why will they not change? Because during collision, the forces will be along the normal. Since forces during collision, or you can say the normal reaction, is perpendicular to the velocities that are unaffected. So no matter how big the collision is, these components won't get affected. So we solve this question, we got v1, v2. Your final answer will be, just add them back. So this is v1 and add back your u1 sin theta 1. This guy is going with v2, then add back your u2 sin theta 2. Done. That's your final answer. Make sense? So if you know how to do head-on, oblique is just remove the perpendicular components and add them back. Clear how to approach the problem? So let's see one. I think that will give you a better idea. Top view. Let's say you're playing carom board. We have a coin. Mass m, radius r. It is at rest. So another coin is coming with a speed u. This coin ka mass is also m and r. We'll keep it simple for now. And e is equal to 1. This is the top view. So there are two coins. So instead of playing with the striker, you're playing with the coins. So the distance between them is r. So the smooth floor. Find the final velocities. I hope the question is clear. You're playing caroms, one coin is at rest. You took another coin, same mass, same radius, and you're hitting like this. So the distance between the centers, horizontal distance is r. So after collision, what will be the velocities? What is step 1? Make them touch each other, draw the common normal. Step 1. When they're about to collide, so when they're about to collide, how will the picture look like? They will be touching like this. So draw that picture when they're touching. Draw the normal. Resolve the velocities along the normal, perpendicular to the normal. Keep the perpendicular components beside. Then you take the components along the normal. It looks like a head-on collision problem. Solve. Get the answer. Then add back the perpendicular components. Try. I'll give you a minute, then I'll show you. Find the velocities after collision. And remember, we wrote a statement. Remember, if two masses of two bodies of same mass collide perfectly elastically, The exchange velocity. I didn't write that statement. I wrote something else. When two bodies of same mass collide, they exchange velocities along the common normal. The velocities will not change completely. Only the perpendicular components will get exchanged. The components along the normal will get exchanged. Show you one. Listen. Draw the picture. So this is here. So when you're about to collide, it's like this. So join the center to center. If you join center to center, this distance will be 2r. This distance will be r. So this angle is 30 degrees. I hope everyone got the angles. Then this speed is u. Resolve this into components. So this will be u sine 30, which will not change. And this is u cos 30. There. Now you can split the problem into two parts. So we got a ball and we got a ball. We got this and we got this. This is the normal. This is the normal. This was at rest. And you're going this way with u cos 30. E is equal to 1, mass is same. Here, this is u sine 30. And we know if two balls of same mass, they exchange velocities. So after collision, this guy will start going with u cos 30. This guy will come to rest in the head-on collision. But the perpendicular components, this is at rest. This is going with u sine 30. Now add them back. So your final answer, this guy, this will go with u cos 30. This will go with u sine 30. They both will go perpendicular to each other. Is that clear, everyone, how we did? Making sense? So it looks like a head-on collision, right? The only new thing you did is resolving the velocities along the normal and perpendicular to the normal. Once you got that, it is straightforward from there. Advait, please adjust your camera a bit. Can't see you. Devanshi, clear with this? Shaunak? Aditi? Confused, Aditi? Clear? Vedika? All got this. Let's see one more like this. Now you guys try. Same thing, I'll just change the distances and numbers. So let's say we have a coin, mass m, radius r. It's traveling horizontally with speed u. We have another one here, 2m and radius r. This is going with speed u. E is equal to half. This distance between them is root 3r. Find the final velocities. What is step 1? Make them touch each other. Draw the normal. Resolve the velocities along the normal, perpendicular to the normal. Step 2, along the normal, do head-on collision ka problem. Step 3, add back the perpendicular component. The important thing is to get the angles. Try. I'll give 2-3 minutes. Same as the previous one, just the angles are different, masses are different, and E is equal to R. So little more working. Give it a try and get some water and come. Any answers? Do you guys get the angle? Let's see. So when they touch each other, that is 2R. This is root 3R. So you won't pass with it. So this will be 60 degrees. Sine theta is root 3 by 2. This guy is going with you. This is also going with you. So we need to resolve the velocities along the normal and perpendicular to the normal. So we can split the problem into two pieces. So that is 60. So this is also 60. U cos 60, U cos 60. Plus this is a perpendicular component, U sine 60, U sine 60. So these guys will not change. This mass is 2m, this mass is m, and d is equal to half. So after collision, let the velocities be v1, v2. Conservation of momentum in this direction along the normal. So along the normal, you're taking it as x-axis. So 2m u cos 60 u by 2 minus mu cos 60 mu by 2 minus, because both are in the opposite direction, is equal to mv1 plus 2mv2. M gets cancelled. This will be u by 2 is v1 plus 2v2. This is one equation. Quotient of restitution is equal to half, which is v2 minus v1 by u by 2 minus of minus u by 2. So we get V2 minus V1 is U by 2. Interesting. Now if I add both of them, V1 gets cancelled. Then I get 3V2 is equal to U. So V2 is U by 3. Looks right. Then V1 will be V2 minus U by 2 minus U by 6. V1 will be did I mess up something? Am I getting negative? Did I write something wrong? 2mu by 2 minus mu by 2. That would be u by 2, u by 2. ठीक है. E is equal to half only, na? E is equal to half. V2 minus V1 by U1 is U cos 60 minus of minus U by 2 U.
Well, I think the V2 minus V1 is supposed to be minus U by 2.
Yeah, V2 minus V1 you're saying?
Yeah, I think so. That's what I got. No.
So I took this as 2, this is 1. No, you are right only. U2 minus V1, U1 minus U2 था वो. No, you are right. I goofed up. Because this is your U1, na?
So,
you are right. So U1 minus U2 will be minus U by 2 minus U by 2. So this will be minus. So when you add this, V2 is actually coming 0. V1 is U by 2. Clear? The reason why I got a doubt, you know why? I'm getting V1 is negative. Means see, after collision, this ball is going this way and this ball is coming back again. That doesn't make sense, na? The ball should have gone ahead actually. So that is how I know the answer was wrong. You're done actually. Okay, question. Then just add your answer. So the 2m guy stops. So it will just go perpendicular to it. So this will keep going with u root 3 by 2. The other guy will go with u root 3 by 2 this way and u by 2 this way. That's your final answer. Any doubts on this? All clear with this thing? There, that is how you do. So that's what I was saying. If you know how to do head-on oblique, you will be able to handle. Clear? Let's see one more. So remember that statement. Suppose in the exam they ask you this statement. If two bodies of same mass collide elastically, they will exchange velocities. Is the statement true or false? So I'll tell you the meaning of that statement. Two balls of same mass collide elastically. Let's say they're colliding oblique U1, U2. So if they collide elastically, what it means, does U2 become this become like this and this become like this? You're getting it? When you say exchange velocities, the complete velocity will exchange. That's a wrong statement. Only velocities along the normal will get exchanged. Are you clear? Or you should have said like this. If two bodies of same mass collide in an head-on collision, they will exchange velocities. That is true. If I don't use the word head-on, and if I simply say two bodies of same mass collide and they exchange velocity, there's a wrong statement. Hope you're clear with that. This is another good one. Let's say top view. We got a ring here of mass m and radius r. So divide the ring into 4 quadrants. Let's name them A, B, C, D. So on the ring, there are 4 points A, B, C, D. Now what you did, you took a coin here. Coin ka mass is also same, mass m. And you projected this with speed v, or let's call it u, towards b. Right? Initially, the ground is smooth floor, and initially the ring is at rest. You're getting it? So this coin will go and hit B. Then something happens. The ring will start moving. The coin will move. And it'll just keep colliding continuously here. Can you draw the path of the coin? Or I can even ask you, after what time it will come back to A and all that. But draw the path of the coin. That would be a better one. Or describe the motion of the coin. How will the ring and how will the coin move? Describe the motion of the ring and the coin. E is equal to 1 for all collisions. Are you getting how it is? So on your floor, you kept a ring. The floor is smooth. There's no gravity, nothing there. So you kept a coin at point A and you shot it towards B. So this coin will go and hit B ka point. The ring will start moving. It's an oblique collision. So ring will move, coin will move, and again they will collide, again they will collide. This will just keep on happening forever. The ring and the coin are just colliding forever. Describe the motion of the coin and the ring. Think how well it will move, and then let's try to draw, and we'll see. Here is Srihari. How will both go like both will move, but not the way you're saying. A simple version would be this: if you stop the ring, then A will hit B and B, C, D. So this will keep going in a square. If the ring was at fixed or ring was at rest, but the ring is not at rest. Every time you collide, ring also will start moving. Think. Take a minute, then I'll show you. Listen, ring ka mass is M, coin ka mass is also M, and E is equal to 1. Just now we made a statement. Every time the ring and the coin collide, they will exchange velocities along the normal. Agreed? That's the first statement. You have to be clear. Since ring and coin have same mass, and E is equal to 1, they exchange velocities along the common normal. So let's see how to draw this. So initially the ring is here. The coin is going towards the point B. So let's divide this into two components. Let's this be Vy, which is u sine 45. Luckily, both are equal actually. This is Vx, that is also u sine u cos 45. So as this coin goes and hits the ring, which velocity will get exchanged? Vy will get exchanged. So just after the collision, this is how the picture will look like. It's a little difficult to draw the picture, so listen carefully. So just after collision, the coin will have only Vx ka velocity, whereas the ring will gain the Vy ka velocity. You're getting it? Vy will get exchanged. I'll do one thing, but I'll just change the colors for this also. There. So the coin will go horizontally and the ring will go vertically. Now see what is happening. As the coin is going to the left, the ring starts going up. If you just try to see the motion, this is how it looks. The coin is trying to go this way. And at the same time, this ring is going upward. You're getting it? This is going up with Vy. The coin is going with Vx. It is going towards which point? It is going towards C now. But you're not going towards C actually. You're going straight. The C is coming towards you. And then the collision will happen again. Like this. So the coin will collide with the ring with Vy. Remember, the ring is still going with Vy. So now the collision will happen at point C. Are you getting how will the motion look? The ring is going up, the coin is going to the left, it will come and hit C. Then what will happen? Vx will get exchanged. Then the picture will look like the coin will stop, coin will come to rest, the ring will go with Vx, and don't forget this guy is also going with Vy. That means now the ring will start going at an angle. So next moment, your ring is going like this. And don't forget, your coin is still at the same place. Your coin does not know what is happening. Your coin will still stay there only. This is point D. So basically the coin got the velocity u actually. It's going with Vx and it's going with Vy. Then as the ring starts going up, the coin will still stay there. The coin will stay there. Now the ring will come. The ring is still going that way. So something of this sort. The coin will be in this position. Same level basically. The ring will come and hit the coin at point D. Are you getting this? Now what will happen? Again, they'll exchange velocities. Now the coin will gain back velocity Vy. And now the ring will keep going with Vx. So Vy gets exchanged. So every time they collide, one component keeps getting exchanged. And now what will happen? Now the coin is going up and the ring is going to the left. So your coin is going straight. With Vy, and your ring is going to the left now. Something of this sort. Where it is going now towards? It is going towards A. And then the collision will happen at point A. And then what will happen? You'll get back your Vx and you'll get back your Vy. So here Vx gets exchanged. And now again, this will continue its motion towards B. And this will just keep happening forever. Is this picture clear, everyone? Will the collision not happen between B and C before the coin reaches from B to C? How will it happen? Just look at the statement you're asking, na, Srihari. You're saying how will B and C collide before B reaches C? What is the meaning of the statement? What are you talking?
Sir, it's like the coin not reaching, sir. Like in between B and C, it is circular. So,
Kaha pe? Where it will collide?
sir, the coin is in B, sir, and then it is going towards C.
Yeah.
Then in between, sir, will it not
It
collide?
doesn't collide. No, it won't collide.
Why?
You try to see that, no? Tell me why it will collide, then I'll tell you why. Think, na, Reva. Without thinking, why are you just, making statements? Why it will collide? You tell me.
Sir, because it's circular, no? So there are many
So it will
points.
collide. So,
It can collide, sir.
Arey God, if you go and stand on the ring, right, with respect to the ring, this is what I told in the beginning. If you stop the ring, what will the ring think? This thing is just bouncing inside, right?
Yes, sir.
So then how it will collide with any other point other than ABCD? If you
Oh,
stand on the ring, how will the motion be? ABCD square.
yes, sir.
So that means with respect to the ring, if you're colliding at ABCD, that means in the ground frame also you'll collide at ABCD only, right?
Why?
Think. I'm giving you time. Exam I won't be there to say why. Think.
Yes, sir. Okay.
Seriously? Why? Tell me. I want to hear. Arey God, relative motion, what did you study, Ray? Huh? You're asking something weird only. If A and B, right, in some other frame, if the A and B meet in one frame, don't the person on the ground also think A and B meet in the, in that moving frame? If
Oh,
two
yes.
particles are meeting in a relative frame, that means they're also meeting in the ground frame,
Yes, sir.
right? Are you sure?
Yes,
In the
sir.
ring ka frame, if the particle collides A, B, C, D, do dekho na, in the ring ka frame, you're touching A, B, C, D. Suddenly, when you're standing on the ground, why will it touch any other point?
Yes, sir.
Making sense? That means, let's say, you come to my house, okay? A person on the road saw you coming to my house. Now, if there's another person who is in the bus, will he see you coming to neighbor ka house?
No.
Same thing, right? If you come to my house in every frame, you're coming to my house only. But is everyone clear what he's asking? It's a decent one. His doubt is like, when you're saying why it will collide with C only, why can't it just collide somewhere in the middle? Right? It's a genuine thing, but the explanation for that's what I was saying. If you go and stand on the ring will always think the coin will collide at ABCD. So if the ring thinks it is colliding at ABCD, a person on the ground also will think the coin is colliding at ABCD. Why will it collide at some other position? Is that statement clear, everyone? Clear, na, Advai? Sidesh? So question is still not over. So can you tell me how will the path look like then? So your path for the coin, initially it is going 45 degrees. Then it lost the vertical velocity. So it went straight. Then it came to rest for some time, right? And then it went straight, and then again it became like this. This is how the path will look like. This is how the coin is going continuously. And how is your ring going? This was there. Then the ring ka center, so ring will go like this. So ring will go up. Then ring will go diagonally. Then ring will go horizontally. This is how the ring is going. Clear with this? But there is one point on the system which is going with constant velocity. Which point is that? Center of mass of the system. The center of mass of the system will continue to go with the same velocity. It doesn't matter how these. So basically, these two. So where is the center of mass for these two? The center of mass for these two is in the middle. This guy will go with some velocity in this direction. So that will continue in that same path. So the ring and the coin will keep going in weird way, but the center of mass will continue in the same path. Is this clear, everyone? And you can actually find the time also. You know how much will be each time here? Again, if you see this speed u and this distance is r root 2, so the time taken will be r root 2 by u. So this will be t0. This will be t. I'll just call this thing capital T. Here t will be 2t. And you will also be here only till 3t. You'll be still there at 3t there. Then you will go to 4t. So 2t to 4t, you will stay here only. There. That's a total time period. And this thing repeats after every 4t, where t is r root 2 by u. I hope everyone clear how I got r root 2 by u. When you go from A to B, what is the length of the hypotenuse? R root 2. What is the speed? U. So distance by speed. All clear with this? Take a break. Come back in 5 minutes. We'll continue from here. Any doubt so far? It's a good one. You need to think a lot. If you see it is just pictures only, if you can clearly see. More to do with visualization. Chal, come back in 5 minutes. How to get 2, 2, 3 T? You got. God, we did na here. देखो ना, coin will be at rest na. So in one path, A, B, C, D, में one side of a square, you are not moving in the ground frame. Right? Each side will take how much time? R root 2 by U. Sure? Yeah. Chalo, let's start off. Come on, everyone. Let's see, this is a good one. So we have a floor here, which is smooth. We have a ball of mass and hits the floor at an angle theta with speed u. After colliding, this ball bounces off with speed v at an angle phi. Find v and phi. The better question is this. Same question, but this time it is rough. So before collision, the ball comes with speed u and hits the floor, and after collision, it bounces off with speed v at an angle phi. Find v and phi. Two cases. Case one, the floor is smooth. Case two, the floor is rough. So the smooth case is a proper mains level question. Rough case will be an advanced question. Let's see. First, let's do the smooth one, and then we'll go for the second part. Everyone should try this. Keep your cams on, everyone. U root square. Yeah, first one is fine. How will you get the second one? Yeah, first one is fine. So let's see the first one. Just now I told you, when you go and hit a floor, only the velocity along the normal will change. So resolve the velocities here. So if you resolve the components, this guy will be, this is also theta. This will be u cos theta. This will be u sin theta. And we saw in head-on collision, whenever you hit the floor with a speed u cos theta, you'll bounce back with the speed of eu cos theta. That means this component will become E times EU cos theta, and the horizontal component will remain same. The component along the normal is unaffected. If that is phi, so this angle is phi. Therefore, tan phi will be the opposite side, u sin theta by EU cos theta. Which is tan theta by E. And what about the speed? Square them and add them. The root over u square sin square theta plus E square u square cos square theta. Done. How will you do the second part? If there is a friction, then what? If there is a friction, then this u sin theta won't remain same. This will get affected because of the friction horizontally. Think, I'll give you a minute or two. How will you handle that? It's an impulse-based problem. Last class we did, remember, a bullet is hitting the block at an angle, something similar. Any doubts on the first part, please ask me. Let's see. Listen carefully. So before collision, speed u, this is theta. This is theta, so this is u cos theta, this is u sin theta. So when the ball is hitting the floor during the collision, what are the forces? There is a normal reaction, there is a friction. These are impulsive forces. So during collision, these forces will be large. So this is the during collision, short, very small interval. And just after collision, you will get two components here, Bx and By. And we know whenever you hit the wall along the normal, your velocity becomes EU cos theta. So this logic is still right. Vx is what I don't know. Clear with this? Whether you're rough or smooth, it doesn't matter. The vertical component will not get affected. Clear with this? Because friction will act horizontally, that will not affect the vertical component. So vertical component will still remain same. It will remain same as the previous one. The horizontal gets messed up. Great. Now in the vertical direction, what are the forces acting? We are ignoring mg because it is non-impulsive. Integral n dt will be change in vertical momentum. So v final minus v initial. So this will be m into EU cos theta. That's your final momentum. Minus of minus mu cos theta because it is coming down. Again, don't worry about the integral. We're not going to integrate anything. This will be mu cos theta into 1 plus a. This is the impulse due to the normal reaction, basically. So the normal reaction on the ground is changing the momentum by this much. Now, if you take the horizontal direction, in the horizontal direction, there is only the friction force minus f dt, minus because it's acting backward. Change in momentum in the horizontal direction, delta px, which is mvx minus mu sin theta. Have a look at the equations. Now, if you take f is maximum, then your equation becomes integral minus mu n dt is equal to mvx minus mu sine theta. You can see the resemblance. It kind of looks like what we did with that bullet and the block problem. Right? And then why will the normal and friction be the impulsive force in the B part also? Why will the, oh yeah, any forces during the collision, you're colliding with what? You're colliding with the floor. So any forces involved during the collision are impulsive forces. The N is always impulsive. During the collision, N is not mg, right? And because N is impulsive, F is equal to mu N, so friction also becomes impulsive. What is the confusion?
Then A part, the normal will still be impulsive. So
Yeah, A part maybe also normal is impulsive, but I didn't use anywhere. In the A part, there is no friction, so horizontal component remained the same. Because of the normal, U cos theta became EU cos theta, right? That story is still the same. Matlab, even if you have friction or no friction, the normal will change U cos theta into EU cos theta. That we didn't have a problem. The problem started because of the friction. Your horizontal component got messed up. Clear with this? In the previous case, there are no horizontal forces, so horizontal momentum was conserved. So because there is a friction here, you can't conserve horizontal momentum. Clear? Yeah. Tanishka, clear so far? Vanshika? Any doubt so far? Then we solve this, substitute. So minus mu, what is ndt? Ndt is mu cos theta 1 plus e. That will be mvx minus mu sine theta. So we get vx is equal to u sine theta minus mu u 1 plus e cos theta. There, this is your velocity in the horizontal direction. Doesn't look that beautiful. Again, there is a trap. Always, whenever you have impulse problems, there is always a trap. This answer is valid only if Vx is greater than or equal to 0. Why? Think about it. If Vx is negative, you know what you're saying? The ball will come and collide like this and the ball will fly away like this. Can the ball ever come back like this? That is not a possible case. So Vx has to be greater than 0, then this equation is right. That is, so we will see what happens if Vx is negative then. Mu into 1 plus e cos theta must be greater than or equal to 0. This will be tan theta must be greater than or equal to mu into 1 plus e. So this answer is valid only when tan theta is greater than mu into 1 plus e. What if Vx is less than 0? So the meaning of this thing is Vx is less than 0. This is what happened. The ball stopped slipping during the collision. And F became 0 in the middle of the collision. Right? Meaning, think of like this. Why is the friction acting in the first place, everyone? If you see, the ball has two components of velocity, Vx and Vy. The reason friction is acting backwards because that Vx is moving, it is slipping. Right? So here Vx is decreasing. And it is slipping basically. So Vx is decreasing in this case. The moment when Vx becomes 0, so the friction is trying to stop you. Sometimes it can't stop you, so it will go away. That is okay. But sometimes the friction is so strong, it will stop you. The moment when Vx becomes 0, now you tell me, if Vx becomes 0, didn't the friction do its job? What is the job of the friction? To stop the slipping. What is slipping? Slipping is relative velocity between the ball and the ground. What is ground ka velocity? 0. So when the ball ka velocity becomes 0 and ground ka velocity is also 0, there is no need for the friction to act anymore. F becomes 0. That means the friction did not act for the entire time of the collision. That is what was happening. Friction did not act for entire time of collision. Let's say collision happened for 3 milliseconds, friction acted for 1 millisecond. Collision is happening, the normal reaction is still there. Is that making sense, everyone? So if I have to draw a picture, see, this is how I'll show you. This is the ball just before hitting the floor. Okay, let's call it as T0. Again, I'm just giving some random numbers. The ball started hitting the floor. And in this process, what happened? The body started getting deformed. It's still a collision. The body is getting deformed. Let's say this is T is equal to 1 millisecond. I'll just call it as 1 ms. The ball will have Vx, right? And the velocity is still downward, Vy. Velocity still didn't change. And friction is acting backward and normal reaction is acting forward. Maybe I should change the colors. Then let's say T is equal to 2 milliseconds. The body is maximum deformed. The N started pushing up. Your friction is still there. Your Vy became 0. You stopped moving in the vertical direction, but you're still going in the horizontal direction. Vx is decreasing. So here Vx is decreasing. Vy is also decreasing. Vx is decreasing. Now next moment, N will start pushing up. Let's say T is equal to 3 milliseconds. So basically the floor, right, has become like a spring. It is pushing it up. Now you started getting Vy. Your Vx is becoming smaller and smaller and smaller. It's slowing down a lot. Friction is still acting backward. Right? Let's say T is equal to 4 milliseconds. There is still some deformation. Your Vx has become 0. Your normal is still pushing you because the body is still deformed. You're gaining velocity. At this point, friction becomes 0. Friction will say there is no need for me to act anymore. But the collision still didn't stop. The body is coming out from the collision now. So in this process, it has gained velocity Vy. N is still there. And let's say this time is 6 milliseconds. I'm just taking some random numbers. Next moment, completely, you lost contact with the floor. Let's say this is 8 milliseconds. You're completely out Vy. And this becomes EU cos theta. And your Vx is 0. So it's like the whole collision took 8 milliseconds, but the friction started acting at 4 milliseconds. Are you getting what is happening with the picture? This is what will happen with the ball when it hits the floor. The part of the body which hits the floor gets compressed like a spring. It's pushing it back. Is this making sense? Any doubts on this? So here, so you can see, so the total collision time, 8 milliseconds. Friction stopped acting at 4 milliseconds. Again, just random numbers. So friction doesn't care about Vy, it will only think about Vx. The moment Vx becomes 0, my job is done, I stop slipping. So what will be your equation? Integral n dt, right, will be mu cos theta. This equation is still valid, plus mu cos theta. So this limits will be 0 to 8 milliseconds, right? This will be integral f dt minus, this will be 0 to 4 milliseconds. The limits are not same. So now you won't be able to solve anymore. This will be change in horizontal momentum delta px. We can't solve because the limits are not same. I can't say now, n dt is equal to mu n dt. I can't solve, but you need not solve actually. The problem got over here. So the moment Vx becomes 0, this is the statement C. So if Vx becomes 0, your job is done. That means if you got Vx negative, it means Vx is 0. So if Vx is less than 0, this implies there is no horizontal component. So this will happen when tan theta is less than equal to mu into 1 plus C. So your final answer will look like this, everyone. So Vx will be u sine theta minus mu into u cos theta 1 plus E 0. This is valid when tan theta is less than equal to mu into 1 plus E. This is valid when tan theta is greater than equal to mu into 1 plus E. So you know how will the picture look like then? The picture will look like this for the second case. The ball is coming with speed u. It hits the floor. Because Vx is 0, the ball will fly vertically upward. It will not bounce off with that angle. It will fly vertically. The phase angle phi will be 0. You're getting how will the ball come? The ball will come hit the floor. It will go up. It will not bounce like this. It's flying up. Because Vx is 0, there's only Vy component. Since Vx is 0, ball flies vertically. Clear with this? That we did it in detail, but exam mein, right, depends. They'll give you the theta ka value, mu ka value. So you have to check always. So after doing this, first of all, this is a tough one. After getting this, the answer is not over. You need to check. If Vx is negative, I explained you all the story. That's why it looks big. But you can simply make the statement. If Vx is negative, that means it can't go back. So Vx is 0. Done discussion. Clear with this? Any doubts on this? It's a good one. Definitely make sure to try it again. Let's see. One more. Last one for the day. We have a particle projected with speed u and theta. Coefficient of restitution is E. All keep your cams on. So this thing goes, hits the floor. Because of coefficient restitution, it will again bounce, falls on the floor, and so on. Let's say the first one ka range is R1, the second ka range is R2, the third ka range is R3, and so on. Find the ratio R1, R2, R3, R4. R1 is to R2 is to R3 is to so on. So a particle is projected at u theta. The floor is not elastic, so there is a restitution. So every time you hit, you lose energy. Find the ratio of the range. Floor is smooth. If I don't say anything, smooth floor. Rough floors are like, they have to mention it. Let's get this. It's an easy one. Right, Samyak. Right, Arya. You know, the same question I can ask like this also. There is an incline and the ball is dropped from here. Then E is there and it bounces. There also I can ask you, find the ratio of the ranges there. That will be even much better. Because in that case, there will be horizontal axis in G sine theta. So how do we do this? So when you're projecting the particle, what are the velocities? U cos theta and U sine theta. So when you fly up and you fall on the ground, now see, every time you hit the ground, only the vertical components will change. So this is U cos, this is U sine theta, this is U cos theta. Standard projectile motion, the horizontal components don't change. And just now we saw, after collision, what will happen to your velocities? After collision, your velocities will become, this will become U cos theta, and the vertical component becomes EU cos sine theta. So every time you hit the floor, your velocity becomes EU sine theta. And then when you come and hit the floor again, this velocity becomes E times EU sine theta, that is E square U sine theta. The horizontal component is unaffected. So only your vertical component keeps getting E times, it gets keep multiplied. So what is the first range R1? R1 will be horizontal velocity U cos theta into time of flight. So U cos theta, time of flight is 2U sine theta by J. What about the second one? U cos theta, and what is the time of flight? 2 EU sine theta by J. What about the third one? U cos theta and time of flight will be 2 E square U sine theta by G. You can clearly see there, the U cos theta remains same. The ratio will be 1:2, E is 2, E square is 2, E cube is 2, so on. Clear with this? So I think when you go for Rn, this will be E power n minus 1. That will be the ratio. This will never stop actually, meaning it will stop, it will do infinite collisions though. All got this? Easy? Any doubts on this? Great. So with that, we'll wrap up for the day. So next class, when we catch up, we'll continue from here. We're almost there. Like we will do a few more problems on oblique collision, and then we'll do variable mass systems. So next class, we will wrap up the chapter. So it's almost done. So you can start solving on this. I will also send you a small practice sheet on this, so you can work on that. So we have done almost 49 questions. So make sure to go through the whole thing, resolve the questions that is important, right? And okay, with that, we'll wrap up for the day. So I'll see you guys again next week on Tuesday, same time. So, and there's a test online. I think tomorrow is the deadline, right? So make sure to give it.